Hello everyone, my name is Adam Lindberg and I work for Cresters here at GmbH. And our talk is about a hardware system that we've developed for building embedded applications with Erlang. So, first a bit of background and a history of why we got into this in the first place. We have a product called HydraProg, which is for flashing automotive ECUs. So basically hardware components for cars, talking special hardware protocols and stuff. And so this system can be used for flashing equipment for manufacturing or flashing big stock with new firmware, for example, in a production line or something like this. So this system is built on a industrial FreeBSD motherboard, which runs FreeBSD and Erlang. And then we have these gateways which talk to the ECUs, and they implement all the hardware protocols. These run an operating system called RTEMS, and then we talk to them over USB. So basically, the gateway talks hardware, automotive protocols, and then it goes over USB to the Erlang side of this FreeBSD industrial motherboard. And there's a lot of those gateways because those are the ones that actually interface with all the components. So you plug them in and out of these, and then you have a central managing Erlang node in this FreeBSD system. So while this left part is in Erlang and the right part is in C, we can look at this operating system that we're using and see if maybe it's a good fit for Erlang as well, because the more Erlang we have, the better. It's easier to work with, it's more high-level language, and we don't have to drill down into such low-level C stuff. So, what is RTEMS? So, it's a hard real-time operating system, and we're using operating system here in quotes because it's actually a executive that you build into your application. So, let's say you have a program. Let's take a C program for simplicity's sake at the moment. You actually link in RTEMS as libraries, and you compile everything into one executable. And you can put this executable and you can boot directly into it from hardware. It's a very minimal, lightweight system. It supports like really low system requirements, like 32 kilobits of RAM and a 12 megahertz clock, so it's very tiny. But it doesn't really fit Erlang. So it's not so important for us, these characteristics, but it's very efficient in switching threads. So it's fast context switching, which is used for Erlang, and it implements a POSIX API, which makes it really easy to port Erlang to it as well. It has some other embedded APIs as well, which could be useful for hardware stuff, but for us, POSIX is interesting. And this kind of concept in general is actually nowadays often also called unikernels. So it's basically you boot directly into your software, you skip the whole operating system, and you just provide the minimal amount of compatibility that you need. As I said before, there is easy fast context switching, but this system doesn't have any processes. So a process and a thread, if you don't know the difference, a process is a managed memory activity running in an operating system, and a thread is a concurrent separate activity inside a process which shares the memory with the process. So if you start up in a normal operating system, if you start up two processes, they can only talk to each other via pipes or something, they can't really share memory. But the thread inside a process, or a bunch of threads, they can share memory. So RTEMS only supports one process because it's just one executable that starts one program, but it does support threads, which means there's like no virtual memory, there's no memory protection, everything happens inside this one memory space. But this is useful because the goal is to just run one program directly on hardware, in our case the Erlang VM, so it's no problem for us. It runs on basically all 32-bit architectures, can be adapted to 16-bit and also 64-bit stuff. And it has SMP support as well. So in this hardware board we're currently building, we only have one core, but there are of course mobile processors that support more cores, so maybe this is also interesting in the future. So as I said, in this HydraProg product we don't have Erlang running on the gateways, but it's a good fit for embedded. And maybe we can then combine Erlang with RTEMS to give you an executable that boots on real hardware, but actually runs Erlang directly on bare metal, which would be really, really cool. So we've been working with this, and the idea is basically that you have your Erlang code running inside the Erlang VM, just as in any other Erlang VM on any other machine or operating system. And the Erlang runtime runs your Erlang code, and we have these drivers that then talk POSIX to the operating system, and this, in this case, would be implemented by RTEMS, these POSIX calls. You can stick a C application next to this if you want, if you manage to link everything into this one executable. So if all of this compiles and you test that it works, you can stick other C code in there as well. And we also support, basically it also supports NIFs and LinkedIn drivers. So normally when you use these in, let's say, Linux or Windows or some other operating system, those are separate files that you load into the Erlang VM. And that's because on this operating system you support dynamic linking, so you can load libraries in runtime, and the operating system manages this for you. But in our case, we are only allowed to do static linking, since it's just one big executable. So the difference here is that if you want NIFs and LinkedIn port drivers, they have to be linked into the application itself at compile time instead. RTEMS also allows you to, for example, to network, so it implements a really small TCP IP stack, but you have some choices in RTEMS. So you can actually use up to the, I think it's 3 different stacks, and one of them is the current FreeBSD TCP IP stack as well, so you can get some kind of nice bigger choices there. And these NIFs and LinkedIn drivers, they're nice because you actually get very low-level access to your hardware, because these, if you write some C code or whatever that talks directly to the hardware, there's nothing in between. Like, you're literally alone with the Erlang VM and the C code inside the VM, let's say a NIF or something, and talk directly to the hardware. And you know when the Erlang VM will be preempted because there's no other processes running on this operating system. If there is an interrupt coming from hardware, you know it will be taken care of in this context directly. So it's easier to do soft or even maybe some hard real-time stuff with this. So we've been using this in a setup at a company called Bosch Rexroth, which is a subsidiary of Bosch. And there we have a project where we build smart transport controllers and smart conveyor belts. So these boxes here with the blue cables, they are actually our hardware board that runs Erlang with RTEMS directly on the hardware. So here's a little demo video basically showing, so we have a demo system built up, and everything that is moving here is controlled by a network of Erlang nodes. And it's about 15 boxes. And you can see them, like there is these blue cables going a bit here and there, and then there is an Erlang box connected to this. So it's a demo conveyor belt, it has some sensor detection for lifts and moving parts. It does some RFID checks, for example, to see where components should go and such. And all of this is controlled with Erlang directly on hardware. So the idea here is that we've done this, we know how it works, we've proven the concept, we like working with Erlang for embedded systems, so our kind of goal is to give this back to the community somehow, and all this embedded experience. And of course we can just like open source tons of stuff, put it on GitHub and say, yay, we're so nice, we've done this. But it's a very steep learning curve working with embedded systems in the first place, and also working with Erlang in embedded systems, doing cross-compiling, figuring out all this driver stuff, and so on. So we want to do something more. And also, we could support lots of different platforms. For example, you know, there's Raspberry Pis, BeagleBones, BeagleBoards, all this stuff. Or Arduino or something like this. So supporting the bigger ones like Raspberry Pi and BeagleBone doesn't make so much sense because they're actually fairly powerful. They can easily run Linux and Erlang, and you don't really need to get the like low-level access to the hardware, or you don't need that performance cut. And Arduino and other smaller things, they're way too tiny, so you don't fit Erlang in there anyway. So our kind of idea was to find the sweet spot in between where you have a sufficiently large embedded system that fits Erlang, but also has lots of great connectors for working with embedded systems and doing like Internet of Things and robotics and such. So we want to design a hardware platform together with the tools and drivers, software that you need to get started developing applications in this. So our goal is to create this platform where you can do embedded development with Erlang in an easy way. So this is the board that we've developed. It's a small hardware board. It's this one here, this size. So it's the current iteration, the current development size. And it has a Apple ARM CPU, so it's a Cortex M7. It's kind of the largest mobile low power ARM that you can get nowadays. 32-bit CPU with some nice stuff on top, like an FPU and floating point unit and some other things. I'll go into a bit more details later. Maybe you noticed that like there's no Ethernet on this, so we thought, okay, let's put something nicer like a Wi-Fi, because in the end, when you build like Internet of Things or maybe some robotics, if you want to fly a drone or something, it's kind of nice to have wireless, and it's way more hassle to get Wi-Fi on top of existing hardware that doesn't have Wi-Fi than the other way around. So we do support, of course, plugging in an Ethernet adapter, but the Wi-Fi is there from the get-go, so you can start building wireless applications. It has a SD card slot, and this is, of course, where you boot your system from and plug in your application. The memory on board is only 300K on the CPU, so we also put SD-ROM on top, 64 megabytes, because the CPU supports this. And this is plenty of space for an Erlang application. These boxes I showed you earlier with the conveyor belt, they also have this same amount of RAM, and there we never really like came close to the limit at all. So there's plenty of space. Maybe you can even put like a database on there inside. Anything you can compile into this single executable. Of course, it depends on what you use it for and what kind of application you build, but 64 megabytes is a lot for Erlang anyway. There's a USB power connector, so you can charge it via your laptop or an external battery pack, something like this. And this also has a JTAG debugger via serial console, and it has serial console as well for the whole board. And there is also a specialized JTAG debugger connector in the lower left there, just above the circle here, if you want to do a hardware connection for the debugger. So user interface-wise, there's 5 switches in this, so you can put them on and off. And there is a switch for the JTAG as well, the 6th one there. And for user output, we support 2 LEDs, so it's a very high resolution display, 2.1 pixels. But it's RGB LEDs, so you can control them using a pulse width modulation or something like this, and yeah, use them for different status things maybe. So next, we have a bunch of hardware connectors. So on the top here, we have PMOD connectors, and it's a standard by Digilant, and it has like 80 plus ready-made components you can buy, and you just stick them into these slots, and then you can interface with them directly. And I'll show some more examples of such components. So these ports, we have 2 GPIO ports here in the top. We have one UART port here, and then we have 2 SPI ports. So one normal SPI port. So SPI is kind of like GPIO, general purpose I/O, but it's a serial connection, so you can chain things up and attach even more things to this. And we have a extended SPI port, which has like a double set of connectors with interrupts as well. So you can have a device that sends you an interrupt, and then you can go and fetch more data when something has been read or when the device is ready. We also put a Dallas one-wire connector on this, which is kind of also another serial protocol. I will explain it later, where you can also hook up more long-range types of sensors too. So yeah, this is the whole board. There's a reset button here, some other useful stuff. So as I said before, it's a 32-bit ARM Cortex-M7, and it does support DSP extensions, but you need a driver somehow for this, and we're looking into maybe providing this via NIF or something, so you can use it from Erlang. 300 megahertz, has a FPU built in, and the goal is that most of these things should be easy to access from Erlang. I mean, this is true for the whole project, that we want to give people the tools in Erlang to avoid having to drop into C unless you do something really, really fancy. Memory, so there's flash memory, 2 kilobytes, or 2 megabytes. This is used for the bootloader, which coincidentally is also built with RTEMS. So this is your static on the ship. And then we have some SRAM, as I said before, 384 kilobytes. And then we put this SD-ROM chip, 64 megabytes. We have the micro SD slot for the system. And then also EEPROM for storing persistent stuff, like some configuration or something you want to stay on the hardware during reboots or power outages. So the GPIO ports, so these are the black connectors on the top. So it's a couple of digital I/O lines, actually. The driver support for this is pulse width modulation. So this is basically it's a one-time configurable wave function that you create, and that will basically switch them on and off in some specified interval. So one example of using this is, for example, driving or controlling some LEDs. So if you have an RGB LED and you want to, you can normally show like 7 colors or turn it off. But with this one, with pulse width modulation, you can then control the RGB channels completely dynamically and get the whole color spectrum, basically. So this is really useful also for like servos and other motor controls and such. We have the switches on the board, the tiny ones. So it's on-off, and you can read them by a register from the board. And you have the reset button in case everything goes bad, crashes, and you want to reboot the whole board. All the switches and stuff and everything else will be accessible via Erlang APIs to make it simple. Then we have the SPI and I2C interfaces. So it's a serial interface to save some I lines. So the CPU only has a limited number of pins, and if you want to hook up even more things to this, you need something like a serial interface to chain things. So it needs less wires. SPI usually has 4 wires, and it's a master-slave protocol with master output-slave input and master input-slave output lines, so 2 ways. And there is also a clock line that determines when data goes in and out. So chips have specifications of when they are reading and writing, and then you have to basically sync to that clock and figure out when you should read or write from one of these components. And there is also a chip select line that you can use to chain even more chips on the same line, and then use this to drive which chips gets to read and write on the same line. Then there is I2C, and this is a bus protocol, and it has 2 lines, so it's data and the clock line, and then also power and ground, of course. You always have power and ground. And this is also a master-slave protocol. The good thing about this one is that it has addressable clients, so you can send data packets to one of the clients or one of the slaves on this line, and they will be able to pick it out from the wire, basically. And all of this is usually for board local stuff, like stuff that's close to the hardware board, because reliability over longer distances is not so good if you have disruption on the line or noise on the line and stuff like this. And that's where the Dallas one-wire protocol comes in. So it's cool because it only needs 1 wire and ground, always ground, but that's why it's called 1 wire. So power and data goes over the same wire, basically. And so either you send data or power, or you can actually take power from the data. And then you have usually a capacitor on the device that stores power. Like if the data rate is low, you can then leech power when the data rate is high, and then keep it alive when the data is low. So it's a really cool implementation. And it's similar to I2C, but it's much longer distance and longer range, because it has like built-in checksums and some other things for data integrity. You have a 64-bit ID for every component, and it's a worldwide unique ID. It's kind of like a UUID or a MAC address or something like this. So if you have a component and you know this 64-bit ID, you can address that component on this wire, which means if you have one of these boards sitting somewhere and then you have a couple of temperature sensors in a room or in a house or something like this, you know, you can identify which one is which and what type it is and so on. There is also, since built-in device discovery, you can see which devices are on the line and you can match them to your specifications or figure out which one has which ID. So the form factors for the Dallas one-wire stuff, it's usually this one. It's kind of like the old-style plastic transistor size and 3 pins. And this is most of the stuff is like temperature sensors or other climate sensors. Then there is an I-button device, which is it's a one-wire device kind of inside a metal button. And you can use it for access control and stuff like this, so key fobs. There are devices that have like memory and some simple cryptographic primitives on chip in the device, so you can store and read and write stuff cryptographically secure. So it's used for authentication and security systems as well. But most of it is usually climate related, so temperature, humidity stuff, simple measurement sensors like this. Here are some examples for PMODs. So I'm just going to go through a couple of them. The first one is a magnetic compass, so you can show the direction of the board or wherever you have this component in. Then we have a 2-ampere motor driver for powering motors. And together with this one, a 4-port standard RC servo connector. So it supports like pulse width modulation for a servo, so you can control like angles or power and different alignment stuff. So if you're building for a drone, this would be useful for maybe tilting some stuff or whatever. Then this one is a GPS, so it's a bit larger. It's kind of a full-feature GPS. I don't know all the features, but it's very nice and comes with lots of GPS-related stuff. And you have a 3-axis accelerometer and a 3-axis gyro. So using these two, for example, you can do drone stabilization or movement detection or anything else related to physical orientation of the hardware. And these are just examples. So as I said before, there's like 80 plus different already made available components. And it's an easy way, if you use this, it's an easy way to get started working with sensors and actuators and stuff, because you don't need to compile anything on your own, you don't need to build anything, everything is just plug and play kind of. And it's a good entrance then to doing more complex hardware designs that you may then later want to print on hardware, but in this case you can just play around with them. So it's easy to provide drivers for these. You have, because they're standardized. And the idea here is that we provide low-level C drivers, and then we build high-level drivers for the various PMODs in Erlang. So we implement the standard interfaces in C, and those you could also use if you have your own connectors, or if you want to use like a PMOD that's not supported out of the box. And then we build high-level drivers in Erlang for the most common components as well. So those are also accessible. So I'm gonna try a little demo here, basically showing the board moving. So we don't have Erlang running on this yet, because we're still compiling it with RTEMS for this hardware. So this demo is gonna show booting RTEMS on it. So this first boot here just blinks, so I can reset it so you can see. It boots and then it tries to figure out something to boot, and then it's blinking red because I don't have an SD card put in. So I'm just going to put in a sample application that uses the LEDs. So this one will RGB cycle the LED. That's all it does. It boots and does this. But it's very fast. You can see it starts blinking the LEDs almost immediately after the reset button is pressed. And then we have one which uses the SD card a bit more. So this is another sample application. It also just lights up the LED. Doesn't blink it or anything this time. But this one is useful to demo the serial connection. So let's try this. Let me know if the size is okay. Is this a good size, or should I make it larger? Larger. So you can talk to this serial devices, and you can use screen to do this. And in this case, I'm also setting the baud rate to get the right input/output. Otherwise, you just see garbage here. And this will drop you into a. I thought it would drop you into a console. Yeah, there we go. So this is the boot process. And this is it, like now we're booted and fully running. I can show you again just to get a feeling for how fast it is. And that's it. So it's about like a second boot time. And with Erlang, it's currently about 3-4 seconds, but we can also optimize this, so we haven't spent so much time there yet. This drops into a very simple shell that RTEMS implements. Kind of tiny. Has some different built-in commands that looks like a Linux shell, but it isn't really. And this particular build, this image that we booted now, has SD card support. So you can see this media folder here in the root partition. If I would show you the other one demo with the RGB LED, you would just see dev and etc because it doesn't have any SD card driver. It still boots from the SD card because the bootloader supports loading it, but the application itself, which contains this shell, cannot do it because there is no driver. This image here has this driver on, which means we can take a look at the SD card. So it's this one, MMCSD. And there's no auto-completion or anything because this is a super simple shell that you get with RTEMS. So yeah, there's some Mac crap on there, and then there is the Wifi file, which is actually the built RTEMS image. So the Erlang VM would also be this bin file, basically. And then when you put Erlang code on this, you would put it next here on the SD card. So you put an Erlang release with all the bin code and everything you need to load, any other files you need. And this would be the Erlang VM, this bin file, which will boot up Erlang and then find your Erlang release and start up on it. And the idea is also that when you run Erlang, or basically when you have Erlang, the Erlang being compiled together with RTEMS, we don't provide this shell here, but we will provide the Erlang shell. So actually we would boot directly into an Erlang shell. And Erlang has like LS and stuff, but maybe we need to add some more features to this to make it a bit more functional, because this shell won't exist once Erlang is compiled together with RTEMS. So that is the demo. So to make this even more easy to get started, as I said before, we want to provide basically the tooling around all of this as well, not just open source some bunch of stuff and hope for the best. So we want to have rebar plugins for creating new Grisp projects out of the box, and for building Erlang, statically linking NIFs and port drivers. So if you just want to build a pure Erlang application, or let's say you're happy with the drivers that comes out of the box that we provide, you're basically good to go. Like you can do rebar, create a new project, dump some Erlang code in there, compile the release, and then push it to the SD card together with the built Erlang VM binary that we provide. But if you want to have NIFs or port drivers, I said it before as well, you need to link them into the Erlang VM executable itself because there's no dynamic loading of libraries here. And then we have to basically develop support for this as well on the tooling side. So we aim to have a plugin for actually pulling down the OLTP source code, putting in all your NIF drivers, linking everything, and then building the whole new binary executable that you can then push as the bin file into your SD card, together with your Erlang code. So this is the way you get your own C code into this project. And you can do this pretty easily with Erlang, so a big thanks to the OTP team because it's pretty easy to actually statically link NIFs instead of dynamically loading them. And we want these things to be as easy as possible when we develop hardware or when you guys want to develop on this board, because there shouldn't be any magic or secret stuff you have to know or things you have to try out. So this should just work out of the box. And because we build this ourselves and we support this hardware, it's hopefully easier than having to maintain like a project like this for many different platforms like Raspberry Pi or BeagleBoard or something like this. So you can tailor it a bit more closely. So Erlang distribution, of course the goal is to cluster these things as well. So we have Wi-Fi and we want to make the Erlang distribution build work over Wi-Fi, of course, it's just a network. So there are some ongoing projects together with Ericsson. One of them is to increase the number of nodes that you realistically can have in distribution. Right now, Erlang is kind of a star network, mesh network, so every node you add will exponentially add load to the system or network load to the system. And we also want to make it easier to have different types of Erlang distribution connections, like encrypted connections. So if you're running this on your own Wi-Fi, it's of course pretty safe, or as safe as you make it. But if you want to run it on a public Wi-Fi or have a device which you connect to the Wi-Fi network that already exists, it would be nice to have some encryption. So let's say you have 3 of these boards you want to put up in a room and you want to connect them to this hotel Wi-Fi. It would be nice if those 3 boards could talk encrypted with each other so people cannot sniff into those connections, for example. And there is also a Ethernet PMOD from Digiland which you can hook up if you want Ethernet as well as Wi-Fi. And one problem we hit was that the EPMD, the Erlang port mapper daemon, didn't run on RTEMS. So the Erlang port mapping daemon is a program that runs next to your Erlang virtual machine, and you can actually see it if you start up an Erlang virtual machine. There will always be in the background some EPMD running. And this takes care of things like if you connect to a host with Erlang, distributed Erlang, and there's 2 virtual machines running with different node names on this host. The EPMD is the one that takes care of finding the right one given the host name and hooking up all the ports and stuff like this. And this is a C program, so it doesn't run next to the Erlang VM on RTEMS or on the Grisp board because there is only one process. So we had a project where we rewrote this in Erlang, in pure Erlang instead. And this got accepted by the OTP team, so it's under the official Erlang umbrella. And this is needed because partly we want to have EPMD running on these nodes, so we have to have it as an Erlang application inside the Erlang VM instead of outside. And it's also needed because if we want to switch distribution semantics later, having different types of channels, we want to be able to do that inside this EPMD, so it's easier, and this has the capability of adding more protocols later. So, this is kind of it. So we want to make it easy to deploy these things, build applications, and we are using the Beam virtual machine, the Erlang virtual machine. So actually any Beam language could be used for developing embedded applications. We'll not support every language out of the box with tooling because it's limited by our effort and time. But we are of course happy to take contributions. Maybe there will be wrappers in other languages for interfacing with the Erlang APIs that we've developed and so on, and some nice tooling for Elixir or Mix or something like this. So just get in touch if you're working on something like this, and it would be cool to get contributions there. Yeah, images used in the presentation. And we have have a mailing list where we will announce when the boards are basically ready. So the goal is that they should be kind of accessible and low cost, and the current price is 100 euros. But the more pre-orders we have, of course, the lower the price will be. And we're also willing to give out boards if you are a student or a teacher that wants to do some project. So if you send the project description to us, we can then send you a couple of free boards maybe. So there is a raffle that we have running, and if you go to the Grisp webpage and if you sign up before Saturday or until Saturday the 26th, you can take part in one of 10 boards that we will give out for free. So please do this. And that's it. Any questions? Yes.
Actually, a lot of them. It's really fascinating. I love this kind of stuff. How many PMODs can you connect to one board? Like 4? Because you have 4
so it's 5 connectors out of the box. These different ones. But since we also support SPI and I2C, you can then change even more of them, or chain even more of them with cables. But I don't know if there's any upper limit to this in the protocols themselves. I don't know the details there. But technically, I mean, if there is a upper limit in the address space or in the amount of wire you can have before it breaks down, that's one limit. And then also the CPU power to run all those things. But it's definitely more than the ones that are here because you can then chain them. And then there's the I2C as well. The Dallas 1 wire as well to hook up even more things.
I like this kind of stuff, and I understand that for industrial usages you have like different requirements. Do you plan to use this for your industrial projects, or is this something like?
I mean, it's pretty early stage, so I wouldn't say like we didn't develop this completely to replace all of our industrial stuff, because they often have other requirements as well. But it could either be useful as a prototyping board, or maybe if you stick this in an enclosure and you have the right input-output, it can also be used for this. So, like power-wise and CPU-wise, it's totally powerful enough to do lots of things like this. And yeah, I think so. It's like we want to make it easy, generic for people to use to build embedded systems, wireless hardware stuff, Internet of Things, and of course, then it will be useful for us as well. Maybe if it's only used for 80% of the cases, it's still good, right? So you might have to drop down into special configurations otherwise. But yeah, that's the goal.
So
yes.
You said like you want to develop something between Arduino and Raspberry Pi, as I understand.
Yeah, kind of.
It should be better than Raspberry Pi in this case, but it's more expensive. Do you plan to make it less expensive, or what advantages
I can't say we plan to, but obviously the more people who buy it, the cheaper it will be on the one hand. And on the other hand, so we basically have a contractor that builds actual hardware, and they have their kind of limits and how they price things. So we're trying to get it as cheap as possible. The goal is that it should be obviously, ideally free, but that will never happen, but as cheap as possible, right? So we'll not do anything, it's not that we're not earning money on this, we just want to sell it at self-cost and then provide the products around so people can build things. So that's the goal, and whatever like the target price will hit in the end, or if we maybe launch now with a couple of boards, like 1,000 or something, and then later we'll build more and they will get cheaper, I don't really know. But the goal is to make this cheap as possible.
Yeah, yes, I understand, but why do people want to choose this board? I mean, between Raspberry Pi and this?
So it's I would say like the main argument is the connectors. So you have easy, more low-level hardware access to different connectors, and you can plug and play these PMODs and stuff like this. And it's a bit more work to do that on a Raspberry Pi or a Beagle board. And also you have, if you don't do anything special, you also have Linux and you have to find drivers. Here we want to provide everything out of the box, already built in. So that's the ease of use also. Any other questions? Yes?
So you mentioned Erlang distribution. Do I understand it would be possible to connect to like regular nodes running on?
Yes, so I mean it has Wi-Fi or Ethernet if you plug it in, and of course you get the network access. So like Erlang distribution is only one type of network traffic, right? If you can access internet on this Wi-Fi that you're on, or via Ethernet cable, you can of course go wherever you want on any network, or you can do some like a web interface on this hardware board that we can access from anywhere in the world.
you mentioned drones a couple of times.
Yeah.
So have you already played around with the gyroscopes and stuff? If you have enough speed and low latency to maybe even do in-flight stabilization?
So we haven't built a drone with it. We have a couple of the PMODs, or lots of them, to compatibility test with and such. But we haven't really tested it in a real use case scenario yet. The only thing I can say right now is I don't see anything obviously in the way for that. So basically it's a low-level hardware access, there's no operating system in between or other processes, so it should be pretty predictable, I think. And 300 megahertz is enough speed for most simple applications.
I don't know how much Erlang was in there, but the guys from Foyer Labs did a demo of running Erlang in a drone and crashing something, and the drone like stayed still. So I don't know how much Erlang was running on the drone, but if you search for Foyer Labs drone demo, there's something in there.
Yeah, I mean, you can run around so much smaller hardware, and I think like the added overhead of Erlang is not that big. Erlang is soft real-time already, and can be more like hard real-time also on a system like this. Yes?
Do you plan on interfacing with the NERVS project at all, making that build?
Not at the moment. I have to admit I haven't looked at it so much, and I actually don't know what hardware they are targeting or how they are doing that stuff. So maybe if there is some kind of cross-pollination there, that would be totally useful. Either like we provide APIs that they can use, or we implement APIs that they have, so you can port code more easily. We'll see. At this stage, nothing planned yet. Any more questions? Yes.
You mentioned LinkedIn port drivers.
Mm-hmm.
And so, I might be wrong, but I understood port drivers the way that you use a port driver in order to decouple the C code of the driver in Erlang to prevent crashes.
Yes.
Wouldn't that kind of...
That would, of course, break in this case.
So why would you use that?
If you have existing drivers, there's differences between NIFs and port drivers in regards to different behaviors. So maybe you need one or the other for some reasons. Or your existing C code is easier to build as a port driver than as a NIF or something like this. We plan to support both, but of course you lose this decoupling that you would have in a normal operating system because you don't have several processes. Maybe you have something that starts an external thread inside this memory space, and then maybe it's easier to do via port driver than NIF, for example. Other questions?
Do you support hype?
Hype? I don't know actually. I don't think so out of the box. I'm not sure exactly how the compilation is working here with ARM, but I think in theory, if Erlang supports kind of ARM and hype, we could support it as well, but I can't really tell you. Okay, if nothing else, then thank you.